So I guess I'm getting more used to looking at myself while I talk. As I read through the labs that you guys did on Thursday and over the weekend, I realized that some of you kind of missed the mark. That's not necessarily any fault of your own. It very likely is my fault. The lab is not written the way that I would have liked to have it, and it probably could have been a lot better. So, what I want to do today is walk through the lab with you so that we make sure that we all got what we were supposed to get out of the lab, because I saw some people being confused and some people kind of going off the path a little bit. So this video is going to walk through it, make sure that you got what you are supposed to get out of it, and then you're going to fill out a Google form so that I can see if you're actually understanding the material. Don't worry, it's not a quiz or anything. It's just to see if you understand what we're talking about. So I'm going to move to my kitchen and we're going to start the lab. And now, time for some science. Don't laugh at my coat. I don't have a white lab coat, so black it is. So you were supposed to collect about half a cup of water, and I just said some other material. So when I first did it, I used a plate, but for this example, I'm going to use about a half a cup of rocks from outside. So both of these are supposed to start at room temperature. Some of you didn't start all of the materials at room temperature, which kind of threw off the lab. So you were supposed to make an observation. So if I stick my hand in, ooh, feels like room temperature. Oh yes, these rocks also feel like room temperature. Write it down in your note sheet. Now, let's put them in the freezer. Excellent. And now we set a timer for 10 minutes. Hey Siri, set a timer for 10 minutes. No. Oh, Siri. All right, it's been 10 minutes. No more, no less. It's been 10 minutes. I'm going to go get the stuff out of the freezer. All right, so first my water. It's a little colder. Feels a little more refreshing than when I got it out of the tap. Not that cold though. Ooh, these rocks are feeling cold. Definitely not at room temperature anymore. So I'm going to go write something in my observation sheet. Now back in the freezer they go for 2 hours. Well, that took a while, but thankfully, timer's up. Time to get it out of the freezer. All right, so if we look at my stuff, I have my water, which is obviously now turned into ice. There's actually a little bit of liquid water still in there. You probably can't see it, but there is. And then I have my rocks. So I need to leave them out for 10 minutes. And then I'm going to do my last observation. All right, so the final observation, 10 minutes later, the ice is still definitely ice. There's a little bit of melty water on the edges. And the rocks, they're still cold, but they are starting to come back to room temperature. They're not as cold as they were when I first took them out. So what this is showing me is that the water is able to keep its temperature a lot longer than these rocks are. It's going to take probably an hour or so for this whole thing to melt. But in an hour, these really should be back at room temperature. What I should have had to do was to have another observation an hour later to see what the deal with the ice was and what the deal with the rocks were. Whoops, you couldn't see those. So that wraps up our experiment. All right, so what you should be taking out of this lab, other than that I should be a movie producer, is that we used 2 different substances that we both cooled down in the freezer and then heated back up by just leaving it at room temperature. And that was water and your other substance, which might have been rocks or a plate or something else. But that is supposed to be representing the land. So we're talking about the water versus the land and how water heats up and cools down versus how land heats up and cools down. So I'm going to write rocks up here, but know that if you use plate or whatever, that's what section it is. And that represents the land. So when we put this stuff in the freezer, after the first couple minutes of being in the freezer, the water really wasn't that cold, but the rocks were. So 10 minutes, the water was like cooler, but not, I wouldn't call it cold. So I'll call it cool, but the rocks were cold. After 2 hours, the water was frozen, really cold, and the rocks were cold as well. The rocks really aren't going to get any colder because they don't have a structure that can freeze like water can. So the rocks were cold, and then they kind of stayed cold. The water was cool, then it froze, and then when we took it out of the freezer, the water, even after 10 minutes, most of that water is still a frozen ice chunk. Whereas the rocks or the plate really should have at least started warming back up to room temperature. It didn't stay that frozen coldness, so warming up. And if we had done this in class, we would have actually been able to take real temperatures instead of using these relative words. But this is kind of what your data sheet should have looked like. And you should have noticed that the water took a long time to cool down and a long time to heat back up, whereas the rocks cooled down quickly and heated up quickly. I also tried to get you to understand this similar phenomenon by doing the frying pan grilled cheese lunch and macaroni and cheese example. Realistically, I probably should have had you do it because most people got it right at the beginning that the fry pan would be really hot at the beginning because it heats up quickly. And the water, as we all know, takes a really long time to boil. What most of you missed was that if I let all that stuff heat up and I let the water come to a boil for like 20 minutes and then I turn it off, If I go back in like half an hour, the fry pan actually will be pretty cool. Like I could touch it and pick it up and bring it to the sink and wash it. The water, it wouldn't be boiling, but it would definitely still be warm. So the pasta water and fry pan example is kind of the same as this. The water heats up slowly and then cools down slowly. And the rocks or the fry pan or the land, they are able to heat up quickly, and then they also cool down quickly. Depending on how quickly it heats up or how quickly it cools down, deals with the amount of energy that you have to put into the system. So if something is going to heat up slowly, that means you have to put a lot of energy into it. You have to leave that stove on for like 20 minutes to get that water to be really hot. So that's taking a lot of energy from the stove. So the water takes a lot of energy from the stove to heat up. Likewise, in the freezer would have to be on for like 2 hours in order for a half a cup of water to get to its coldest point into ice. So that is taking a lot of freezer energy in order to cool the water down. On the other hand, the rocks, which is representing the land or the fry pan, when you turn the stove on, it takes a lot less energy to get it as hot as it's going to be. So much less energy. So then we have to go to that word that I introduced, the specific heat. So if something takes a lot of energy, it has a high specific heat because it needs a high amount of energy. So of these two, one of them has a high specific energy and one of them has a relatively low specific, heat, specific heat. So the water, it has a high specific heat, and the rocks have a low specific heat. Every substance has a specific heat, and there's a chart for it. So copper has a different specific heat than nickel, and those have a different specific heat than water. Because if you were to heat up copper, it would heat up a lot faster than if you heat up water. So all substances, they have a specific heat, the amount of energy that needs to be put in to raise the temperature up a degree. So we have our water with a high specific heat, our rocks or land with a low specific heat, and the Pacific. And the specific heat also tells you how much it's going to hold on to its temperature. So if I heat up my water, or let's do the freezer one, if I put it in the freezer, it's going to stay frozen. It's going to hold on to that heat because it has a high specific heat. Whereas the rocks, when you take them out, they're going to warm up pretty quickly. So because water has a high specific heat, it can hold on to its temperature. Hold on to temperature. So this was the example that I gave you where if there was a really hot July day and you went to the beach, the sand is wicked, wicked hot and the ocean is freezing. I have definitely experienced that several times. That's because when the sun is shining, it's the same amount of sun that's shining on the ocean versus on the sand, but the sand is able to heat up really, really quickly, so it gets hot and burns your feet, and the water heats up really slowly because it has a high specific heat. If you go back at night, what's going to change? This is a question that's going to be on the Google form. So think about if you go back at night, what might look different? Why does swimming in a pool in the nighttime always feel warmer than when you swim in the pool during a hot July day? This all has to do with this specific heat and how things are able to hold on to their temperature. So I also wanted to talk briefly about the Burlington, Essex question, because some people got it and some people didn't quite get it, or they wrote something that I think they got it, but they wrote the wrong answer. So I'm going to go over that really quick. All right, so your very brief overview of Vermont geography. We got the Green Mountains running up the middle. We got New York over here. In between Vermont and New York is Lake Champlain. Burlington is right on Lake Champlain. We've probably all been to Burlington and see the beautiful lake down there. Essex is a little bit inland, and then, yeah, that's all that's on my map. So, if we are thinking about Lake Champlain as being a big body of water, my question was, which city, Essex or Burlington, is going to be warmer in the winter? And it all has to do with Lake Champlain. So if we think about Lake Champlain all summer long, collecting that warm heat from the sun, over the summer, the lake is getting warmer and warmer and warmer. It takes a lot of energy to heat it up, so it's never as hot as the air around us, but it is getting warmer. In the fall, the air starts getting colder. The ground starts to freeze. But think about what happens to the lake. Remember, it cools. Water takes a long time to heat up, but it also takes a long time to cool down. So it's actually acting like this big, warm bathtub that's sitting right next to Burlington. And all winter, it's kind of releasing some of that heat that it's been collecting all summer into the Burlington area. So because Burlington is right on the water, it's actually able to use some of that stored up summer heat during the winter, whereas Essex is inland away from it and can't use that water. Some people talked about there being more lakes and stuff in Essex. If you live right on a lake, yes, but Lake Champlain is humongous and it can hold a lot more heat than a small little pond or lake or things like that. So the answer to that question is that because Burlington is on the water, it's able to, and Lake Champlain holds all that summer heat, Burlington is actually, if we only took location into consideration, would be the warmer city. All right, so what I am hoping is that after watching me do the lab, reviewing your thoughts on the lab, and listening to my explanation of some of the things that you should have been learning, I hope that you have a better understanding of what things that have high specific heats and low specific heats have and some of their properties. Another important thing is thinking about the air temperature and how the sand heating up would affect the air temperature above that and the water's air temperature above the water, because that is where we start getting into the atmosphere and how the geosphere and the hydrosphere are influencing the atmosphere. And that's where we start getting into weather. So I have created a Google form. I think, as long as I did it right, the link is in the description or for this video. And I'm also going to post it on Google Classroom so you can get to it that way. So that's all you have to do for today, is to watch this video and then to do the Google form. As always, leave me any feedback that you want.